Hi everyone, welcome back to my channel. I am Divyajyoti Das, and in today's video we are going to discuss the relativistic Doppler effect. The relativistic Doppler effect is a phenomena where the frequency and wavelength of light changes as a result of the relative motion between the source and the observer. Now before I talk about the relativistic Doppler effect, let's take a moment to talk about the Doppler effect in sound, or the classical Doppler effect in sound. So for example, if you're standing on the side of a road, you may have observed that when a car goes past you at very high speeds, the frequency of the sound of the car as it is approaching is different compared to the frequency of the car as it is going away from you. Have you observed that? You see, what happens is, as a car is traveling towards you, the pitch of the sound of the car or the frequency of the sound of the car is actually higher than its actual frequency. And as the car is going away from you, the pitch or the frequency of the sound of the car is actually lower than what is the actual frequency of the engine. This apparent change in the frequency that you hear when a car goes past you at very high speeds is the classical Doppler effect of sound. However, a similar phenomena exists in terms of light radiation. What happens is that if there is some kind of a light source that is emitting some kind of a light wave of frequency, let's suppose nu naught, alright, then if that same signal is being detected by some kind of an observer or a detector, then the frequency that this detector is going to measure is going to be nu. Then this nu and this nu naught are actually not the same. The frequency measured by an observer and the frequency emitted by a source in relative motion are actually different. This is the relativistic Doppler effect that happens in terms of light. However, the reason why this happens is much different from the classical Doppler effect of sound. In the case of sound, the change in frequency happens due to the relative motion of the observer and the sound waves in that particular medium. But in the case of light, the change in the frequency actually arises as a result of time dilation effects. Now, you may have already known that time dilation is one of the central consequences of special relativity. That is, moving clocks appear to tick slowly. Or we can say that the measurement of the time period between two different events by an observer in motion and the measurement of the time period between the same two events by an observer at rest are not the same. The time periods measured of the same events by an observer in motion and by an observer in rest are actually different. This is known as time dilation, and it is a consequence of the time dilation effects that the measurements of frequencies as emitted by a source and as detected by an observer are also different. And I'll show you how all of this happens. But before that, I want to make one thing clear, that in relativity you must have heard of various other kinds of red shifts and blue shifts also. So for example, when the frequency increases, we call it the blue shift. When the frequency decreases, we call it the red shift. So for example, if there is a faraway galaxy that is traveling towards the Earth, the light radiation may experience a blue shift, and if the galaxy is going away from the Earth, the light radiation may experience some kind of a red shift. However, other kinds of red shifts can also be seen in nature. For example, due to light radiation exiting some kind of a gravitational field, or due to light radiation traveling from faraway distances as a consequence of the expansion of the universe. So I'm not going to be talking about the red shift that happens due to gravity or the red shift that happens due to cosmological expansion. So that is something that has to do with gravity. What we are discussing here is the apparent red shift or blue shift, or the Doppler shift that happens due to relative motion only and not due to gravity. Alright, just keep that in mind. So what I'm going to show you is that the frequency as measured by a detector and the frequency as emitted by a source are actually different, and I'm going to derive the relationship between both these two frequencies by this very simple setup. Now it must be very clear from the diagram itself that this is the ground, this is the earth, this is some kind of a detector, some kind of an antenna, and this is a ground observer which is detecting the signals that are being emitted by some kind of a satellite that is traveling at very high velocities at a particular direction. Okay, so I'm going to take the general case scenario where the relative motion is not in the direction of the line of sight, but rather it is at an inclined direction to the line of sight at an angle of theta. If we obtain this general result, from there we can obtain the other results with respect to, let's suppose, longitudinal Doppler effect or transverse Doppler effect. So what we have here is a satellite which is emitting signals or some kind of a radiation which is being detected by a ground observer. Alright. Now these signals have a particular frequency. I'm saying that they have a frequency of nu naught with respect to the source. Now what does frequency actually mean? Frequency simply means that the number of oscillations of the light wave that is happening per unit time. So for example, if you have a very simple light wave, then what is the time period of one complete oscillation? If you know the time period of one complete oscillation of a light wave, then the frequency is simply 1 upon time period. Right? So if the time period of one complete oscillation is t, then the frequency of that light radiation is 1 upon t. So here you can imagine that the satellite is emitting signals or pulses, or you can also think of these as the crest of some kind of a light wave. So as a light wave is being emitted, the crest is associated with one particular signal, the next crest is associated with another particular signal. By looking at the time periods between two signals or two crests, we can obtain the frequency by finding out its reciprocal. Alright, quite simple. So what is happening here in this particular experiment is that this satellite emits one particular signal, and then it emits another particular signal, but by that time it has moved a particular distance because the satellite is in motion, right? So let's suppose that we look at this entire phenomena from the perspective of the ground observer. You see, in relativity, observers are very important. You see, depending upon which observer you are, the entire phenomena may be different compared to if you look at the same phenomena from another observer's perspective. So we have here two observers. One is the observer with respect to the ground receiver or detector, and the other is the observer with respect to the satellite. Now these observers are not necessarily human beings or scientists. They may just be measuring devices. Now I want to make the measurements first of all with respect to the ground observer. So what I'm going to say is that the first signal that is emitted by the satellite is at a time of t1 with respect to the ground observer, and the second signal is being emitted by the satellite at a time of t2 with respect to the ground observer. Fine. Two signals are being emitted by the satellite, one after another, and the second signal is emitted at a time t2 where the satellite has actually gone ahead in its position because it has a particular velocity with respect to the ground observer, and the first satellite is emitted at a time t1. Now these signals will take some time to reach the antenna at the ground. So I say that the time at which the first signal reaches the antenna at the ground is t1r. So this is the time at which the first signal is received by the antenna, and the second signal which is received by the antenna at the ground is given as t2r. So T1 and T2 are the time periods at which two signals are being emitted by the satellite with respect to a ground observer, and T1R and T2R are the time periods at which both these two signals are received by a detector on the ground, one after another with respect to the same ground observer. So let us write a couple of equations which are very much obvious from this setup. The first equation is T2R is equal to T2 plus L upon C. You see, the time at which the second signal is received by the antenna is equal to the time at which the second signal is emitted plus the time it takes for the signal to go through this particular distance. Let's suppose this distance is L and the time period is L upon C. So we are imagining that the light is traveling through vacuum because we are interested in obtaining the most basic equations concerning the relative motion. So we are keeping the equations simple. Similarly, I can say that T1R is actually equal to T1 plus the time it takes for the signal to travel this particular distance, which is what? See, the distance from here to here is actually L, right? But what about this particular distance? You see, in the time period in which both these two signals are being emitted, the satellites are actually moved in a particular direction. So if this is the angle of theta and the satellite has a velocity of v, and let's suppose the time period between T2 and T1 is del t, okay? So T2 minus T1 is del t. So in that situation, this particular distance is v into the time, which is del t. So v del t is the distance that the satellite travels in between emitting two consecutive signals with respect to a ground observer. So if this is the distance that the satellite travels, then what is this particular distance? This particular distance is nothing but the component of v del t, which is v del t cos theta. Okay, so v del t cos theta is the extra distance that the first signal had to travel as compared to the second signal. Now please keep in mind that these distances are very large distances. We are talking about a satellite that is far away and a receiver is at the ground. And because these distances are very large and the frequency is so high that the signals are being emitted one after another very fast, so there is not much change to the angle that has happened for both these two signals 1 and 2. Because of the very large distances between the antenna and the satellite, the angle theta does not change much between two consecutive signals. Therefore, I am going to keep the theta the same for both these two scenarios. So in that situation, the extra distance, this is actually L plus V del t cos theta, where del t is T2 minus T1. So T1R is equal to T1 plus, I can say that L plus V del t cos theta divided by c. That's it. So these are the two time periods between the reception of these two signals, and T2 minus T1 is the time period between the emission of these two signals. So let me just take the difference of both these two. So now T2R minus T1R, this simply becomes T2 minus T1 plus L minus V del t cos theta upon c. So L and L here gets cancelled, and we are finally left with T2 minus 1 is nothing but del t, the time period in which the satellite goes from here to here with respect to a ground observer. So this is just del t minus V del t cos theta upon c. Quite simple, right? And this is nothing but the time period between the signals being received one after another. Let's suppose that is del t r, okay, which can be further simplified by taking the del t out of the equation, which is del t 1 minus v cos theta upon c, and on the left hand side you have del t r. All right, now how can I relate these time periods with the frequency of the light signal? All right, what is the frequency of the light signal as received by the ground observer? That is nothing but the inverse of del t r. Okay, so the frequency as measured by the ground observer is the inverse of the time period as measured by the ground observer between two consecutive signals, right? So this is 1 upon nu, right? What about del t? Now del t is the time period measured by the ground observer. Here I'm going to take into consideration the time dilation effects. See, what is del t? Del t is the time period between the emission of two consecutive signals with respect to the ground observer. What about the time period between the emission of the two signals with respect to an observer on the satellite? With respect to an observer on the satellite, the time period between any two consecutive signals is not del t. It is something else, which is known as a proper time. So if I say that the proper time is, let's suppose, del tau, then what is the relationship between that proper time del tau and del t? Del t is actually equal to del tau upon root over 1 minus v square upon c squared. So the time period between two signals emitted by the satellite as measured by a ground observer is actually related to the time period between those two signals emitted by the satellite as measured by an observer on the satellite by this equation of time dilation. See how time dilation is coming into the picture? So if I include that in the equation, then what changes do I see? The equation simply becomes, here on the right hand side you have 1 minus v cos theta upon c, and now del tau is actually the time period associated with two consecutive signals with respect to the source. So now I can correlate del tau with the frequency of the source. So what is the frequency of the source and how does it relate to del tau? Well, the frequency of the source is 1 upon del tau, so that is nu naught. So nu naught is the frequency with respect to the observer on the source, and nu is the frequency with respect to observer on the ground. So the final equation therefore simply becomes nu is equal to nu naught, and in the numerator you have root over 1 minus v square upon c square, and in the denominator you have 1 minus v cos theta upon c. That is it. This is the formula corresponding to the relativistic Doppler effect. As you can see here, the frequency as measured by the observer and the frequency as emitted by the source are not the same. They are different. And the difference not only depends upon the velocity, the relative velocity, but it also depends upon the angle at which the motion is taking place with respect to the line of sight. So this is the general expression for the relativistic Doppler effect formula for the change in the frequency between an observer and a source. And as you can see that it is a result of the time dilation effects between the source and the ground observer. Now, I can further simplify this formula into quite specific formulas associated with what is known as transverse and longitudinal Doppler effect. So, for example, if the source was moving directly towards the observer or directly away from the observer, that would represent the longitudinal Doppler effect, and if the source was traveling at perpendicular directions to the observer, that would represent transverse Doppler effect. So now that we have obtained this general formula, from here I can obtain both the formulas for transverse as well as longitudinal Doppler effect. So let's do that. Alright, so I have three different scenarios here. So let's suppose there is a galaxy which is traveling towards the Earth, and it is emitting some radiation which is being detected on the Earth. And similarly, a galaxy which is going away from the Earth and it is emitting some radiation which is detected on the Earth. And the third case scenario where a satellite is just overhead an antenna, so that the angle that it makes is 90 degrees. The angle of the velocity with the line of sight is actually 90 degrees. So in these three different scenarios, we can use the formula that we have obtained to get some specific results. Alright, so let's try with the first one. So in the longitudinal Doppler effect, where the source is approaching the observer or the Earth, the theta can be taken as 0 degrees. So if I take theta as 0 degrees, what is cos 0? Cos 0 is nothing but 1. So if I substitute that here, what do I get? In the numerator, I get 1 minus v square upon c square. Nu naught is already there. And in the denominator, I have 1 cos theta is 1, so 1 minus v upon c. So 1 minus v upon c can be written as root over 1 minus v upon c square. So this can simply be written as nu naught. Now I have root over, in the numerator I have 1 minus v upon c. So 1 minus v square by c square is nothing but 1 minus v upon c into 1 plus v upon c. So 1 minus v upon c and 1 plus v upon c. This is a square minus b square is equal to a minus b into a plus b. And in the denominator, I have 1 minus v upon c, which can be written as root over 1 minus v upon c square. So this is 1 minus v upon c into 1 minus v upon c. So here 1 minus v upon c, 1 minus v upon c within the square root gets cancelled, and finally we are left with nu is equal to nu naught root over, in the numerator you have 1 plus v upon c. In the denominator you have 1 minus v upon c. This is the longitudinal relativistic Doppler effect when the source is approaching the detector. Alright. Similarly, if the source was actually receding the detector, in that case theta is going to be 180 degrees. So if theta is going to be 180 degrees, what is cos 180? It is minus 1. So in that kind of a situation, this simple formula will again take the form nu is equal to nu naught root over 1 minus v square upon c square is simply 1 minus v upon c multiplied by 1 plus v upon c. Right, in the denominator we will have 1 minus v upon c cos 180 degree, which is minus 1. So it will become 1 plus v upon c. Okay, so this is going to become 1 plus v upon c. If I keep the 1 plus v upon c within a square root, then I'll simply write 1 plus v upon c into 1 plus v upon c. So here 1 plus v upon c, 1 plus v upon c gets cancelled, and finally we get the formula nu is equal to nu naught root over 1 minus v upon c in the numerator and 1 plus v upon c in the denominator. So this is the longitudinal relativistic Doppler effect for the case where the source is receding away from the observer. You see that the formula here is slightly different from this particular formula. Here 1 plus V upon C is the numerator and 1 minus V upon C is in the denominator. Here it is the complete opposite. And finally, in the case of transverse Doppler effect, theta comes out to be 90 degree, cos theta, where theta is 90 degrees, is actually 0. So this simply becomes nu is equal to nu naught root over 1 minus V square upon C square, and in the denominator you have 1 minus 0, just 1. So this is quite simply put the transverse relativistic Doppler effect. So as you see, when the source that is emitting some kind of a light radiation is either coming towards the detector or the earth or the observer, or it is going away from the earth, or it is traveling at a perpendicular direction with respect to the observer, or it is traveling at some inclined direction with respect to the observer, the light experiences change in the frequency and therefore also change in the wavelength compared to the actual light that is being emitted. This is the relativistic Doppler effect, also known as Doppler shift. So that is all for today. I hope you understood something from today's video, and I'll see you in the next one. Thank you very much.